Well, hello, everybody. Greetings from TLV here in Charlotte, North Carolina. My name is Norm White. I'm the president of TLV here in the US. We're responsible for the market and customers here in the United States and the Canadian region. And very much want to welcome you to today's broadcast. This is the most multinational global event we have ever broadcast. We've had people from over 50 countries sign up to attend the sessions. We have the session today. Thank you for tuning in. This one at 11 o'clock Eastern. And if you can't stay tuned in or you know others that would like to tune in, we'll be broadcasting an encore session here at 2 o'clock Eastern. It's the same registration link. You don't have to do anything different. You don't have to re-register. So just use your same registration button or event button, excuse me, to tune in, and you'll also be able to join this afternoon's session. I'd like to introduce my esteemed colleagues that you see here in the background. They'll be presenting, and one of them will be kind of facilitating, looking at your questions in the background. So first, Alan Ho. Alan, welcome. Alan is sitting in Japan, where at the moment, I believe it is 1 a.m. in the morning. Alan, you look really bright and shiny.
12.
12, okay, I have my timing off, okay. Anyway, it's midnight, so it's tomorrow for you. Alan is, we were just saying, kind of the godfather of this process in the session today, risk-based inspection for steam assets. He's been working on this program for the company for over 10 years. So Alan will be presenting, as well as Justin McFarland. Justin, say hello.
Hello, everyone. Good morning.
Justin is our engineering manager here for the operations for the here in Charlotte. Again, supporting clients in U.S. and Canada, managing all of our consulting team, including the team that comes out and can perform these kind of assessments. Also want to introduce one of our consulting engineers, Alec Newell. Alec, say hello.
Everyone. Hi.
Alec will be coming back in on the backside of today's session. He'll be looking at everyone's questions in the background. We plan to have about a 45-minute presentation, about 15 minutes for Q&A, and Alec will be monitoring the questions and facilitating those back to Alan and Justin as we wrap up today's event. So again, thank you very much for tuning in. We're excited to get the information out to the market. This is not new to us, as I say. Alan and our team, we've been working on this for about 10 years, but this is kind of new to the market, the development that the API risk-based inspection recommended practice has been expanded just earlier this year now to include steam assets. Before I turn it over to the program, a couple of things just for housekeeping. First off, you've got your GoToWebinar control panel. If you're not familiar, there's a couple of ways for you to interact with us during today's event. First, you see a box down there where you can enter questions. It says enter questions for staff. Please enter your question there. That'll be coming back directly. Alec will be monitoring that. And again, if it's something quick, he'll respond back to you in real time, but we probably plan to present or wait to discuss those at the conclusion. There is a button that you see there for raising hands. That's going to be turned on, but please don't use that because we won't be interrupting the session. So please, if you have a question, submit it in this Q&A box. There's also an area we have some handouts for you today. These are articles that are actually posted on our website, but we've actually pulled PDFs down so you can download them directly from today's event. One is an article from Inspectioneering Journal, one from Hydrocarbon Processing Magazine, and a little quick flyer that describes this process. In addition, if you want to expand your webinar window, you have the button there on your control panel that'll expand it across your entire screen. If you want to minimize the control panel, then hit that orange arrow and it'll remove these boxes for the attachments and the Q&A and everything, and you'll just be able to see the presenter's full screen. Before we get started, I want to provide the typical disclaimers here that what we're going to present today are examples from different things that we have seen as we have implemented this program across the globe. They may not be representative of exactly what is going on in your facility. So these are just examples. If you do have specific things you want to discuss with us, please do that. So again, just kind of read through that. I'll give about 15 more seconds. Okay. So with that, I'm going to turn it over to Alan. Alan is going to kick off today's program, and then on the backside, turn it over to Justin McFarland, who is going to get into some specific examples and case studies with us today. All right, enjoy the program today, everyone. Thank you.
All right, so thank you very much, Norm. I'm going to start on the slides and turn off my camera so that you guys can just focus on my voice, right? Okay. So I wanted to start with an incident. This was a catastrophic failure which happened at the petrochemical plants. So here we had 18-inch steam main that ruptured suddenly. It resulted in a very large flow of MP steam directly discharging to the atmosphere. So you can see that the rupture point over here, also marked out on this drawing. So it happened at this T-piece. So of course, it created a lot of structural damage. Luckily, there were no fatalities in this incident, but the plant experienced very significant production losses as several process units had to shut down because their steam supply was disrupted. So what was interesting was that in the subsequent investigation of this failure, it showed that it was the isolation of one very critical steam trap that was located at a low point in the system, which created the conditions for condensation-induced water hammer. That was what resulted in extreme internal overpressure that ruptured the piping. So the steam trap, of course, as many of you should already know, the steam trap, a steam trap is a self-actuating valve that automatically drains condensate from steam piping or from steam equipment. So they are found at regular intervals along the steam mains or on heat exchangers or steam tracing lines or steam turbines. So they serve a critical function in steam systems by acting as a kind of a gate to allow condensate to be removed from the steam space without letting the steam escape. So when there is a functional failure of a steam trap, there are two possible events. It can leak and start passing steam internally, creating energy loss and other problems downstream, or it can fail to fully discharge condensate, causing condensates to back up upstream of the steam trap, which was what happened for the steam trap that was isolated in the previous slide. So when water hammer happens, we can actually look at what is the mechanism and what actually happens inside the piping. So this is a video that was taken by TLV when we generated water hammer. So you can see that when condensate starts to back up into the steam space, the flow of steam can create waves. So that wave, when it creates an enclosed steam space, I'm just going to, So when the steam space collapses, the impact will cause a massive pressure spike. So that's what actually we hear as water hammer. And this is another experiment that TLV we conducted back in 2019. So over here, we used a 4-inch schedule 40 steel pipe in this case. And we wanted to measure the pressure spikes generated by water hammer. So we installed some pressure transmitters along the piping. The system pressure was maintained at around 2 bar, 29 psi. So we controlled the flow of steam as well as the flow of condensates through this piping. And then, well, basically just sat down and waited for water hammer to start. And this graph shows the pressure trend that was measured at one of the pressure sensors. This was for a period of about 3 minutes. Like I said, the operating pressure was about 29 psi, and you can see that the highest pressure, the peak pressure that we measured during the water hammer events, it exceeded 1,500 psi, more than 100 bar gauge of pressure. The only reason we did not measure anything higher was because the pressure transmitters that we were using, they were only rated for up to 100 bar. So this was, of course, more than 50 times, 50 times higher than the system pressure. That was the pressure that was created by water hammer. And as you can imagine, after we saw these results, what we did was we stood up, we moved our chairs further away from the piping before we continued the experiment. Now, water hammer in steam piping and in steam equipment, it has been known to cause very severe accidents and even fatalities. So looking through the accident records from the US Occupational Safety and Health Administration, we can find events that appeared to describe water hammer and events that actually resulted in very serious injuries. Another major and also very public incident that involved water hammer was this event that occurred in New York City in 2007. So in this case, it also involved a large diameter steam main that was flooded because the steam traps installed were unable to fully discharge condensate. So that, again, that's to water hammer, the pipe rupture, and as you can see from the photos, very extensive damages. So there can be very different root causes of water hammer. Broadly, we can categorize them to be issues related to either design, maintenance, or operational. We see here, so there can be issues that deal with failure to ensure condensate has been removed using steam traps. So that was essentially what happened in the previous few examples that I showed. Unfortunately, we do not really have the time today to dive any deeper into this topic of water hammer. But I strongly suggest any of you out there who have water hammer issues, you experience problems in your plants with water hammer, yes, reach out to us, reach out to TLV, and I think that's something that we can help you to resolve. I do want to move on to examples of other steam using equipment where we see failure consequences. So besides water hammer, which of course can lead to a loss of containment, we do also see other failure consequences such as steam turbine failures, heat exchanger flooding, and also heating issues. Failure in steam tracing systems that can lead to product solidification, as well as failures in flare systems and stripping steam columns that can get damaged due to wet steam or condensate slugs. So all of these failures can result in the functional failure of the steam equipment that are critical to plant operation. So all these failure consequences provides a very strong justification for applying a risk-based approach in steam using equipment or steam distribution systems. So a risk-based approach is when we determine the probability of failure, POF, combined with the consequence of failure, COF. So after we identify the risk, we can then evaluate how to reduce or to manage the risk. Now in API 581, the recommended practice provides very clear, very detailed methods for RBI for risk-based inspection. However, actually up until last year, the API 581 standards actually did not include any methods to evaluate risk that is related to the steam traps or to failure mechanisms such as water hammer. And well, exactly 10 years ago, TLV, we started to develop an RBI method specialized for steam systems. So we based it on the principles of quantitative risk assessment as described in API 581. But we also applied our knowledge of steam system best practices and our experiences with steam trap and steam equipment inspections. And we created what we call SSRM, Steam System Risk Mitigation. And to this day, we have implemented these SSRM methods at 28 plants around the world, mostly in the refining and chemical industries, but also covering some other industries. In total, we have performed risk assessments for more than 400 steam equipment, including steam mains, steam turbines, reboilers, heat exchangers, as well as flare systems and steam tracing. And there's also good news because in February of this year, the API 581 guideline, it was updated to the 4th edition. So this was just very recently released. And there are several improvements and changes from the 3rd edition. One major change was that a new section was added for steam system. So it's now included under Part 5, Special Equipment. And there's a new section here that covers the steam system. And this uses exactly the same methodology of TLV's SSRM. So it includes water hammer as a damage mechanism like we saw in the earlier examples. And this change highlights the importance of risk mitigation in steam systems and will hopefully help to contribute to increase the reliability of steam systems in the industry. So next, I want to go through an overview of what's involved in the risk-based methodology for steam systems. Firstly, we start by calculating the base probability of failure for the steam equipment and its associated steam traps. Here we are using the 2-parameter Welbu distribution. The parameters may be from actual failure data or using the references given in the API 581 document. In the case of steam traps, this base POF is then adjusted using probability factors to account for the actual site conditions. So that will arrive at the final steam trap POF. And of course, if there are multiple steam traps involved, their relative configuration is used to calculate the line POF, which we can then combine with the adjusted steam equipment probability of failure to calculate what is the final steam application probability of failure. And then on the other side of the equation, we can calculate the consequence of failure by considering factors such as production downtime, component damage, or injury costs. And then finally, we arrive at a risk value that can be expressed on the risk matrix. So these results can then be used for risk mitigation planning or for cost risk optimization. Some important notes about this approach, first of which is the risk analysis it is performed for the steam using equipment or for the steam main together with their associated steam traps. So what this means is that we get a risk result of probability of failure and consequence of failure for each steam equipment. Essentially, we get one dot on the risk matrix. So if we perform an assessment for 10 heat exchangers, for example, so we can then plot 10 dots on the same matrix. So you can also imagine this allows for an objective comparison of the risk from different equipment in the plants and where priority should be given. Another key note is that for the steam trap probability of failure, of course, there are reference wellbore parameters that are provided in API 581, but it is still recommended to use more accurate data if available. In the SSRM risk assessments that TLV perform, we have a very large database of more than 300,000 steam traps inspected over the course of 15 years. So this allows us to derive more accurate failure probabilities of the steam traps. And then very similarly, in the case of the steam equipment probability of failure, again, there are reference values that are provided in the API documents, or plant-specific data can be used. In the absence of plant-specific data, TLV will use external sources such as the ORIDA handbook or industrial failure data to estimate the base equipment POF. And then finally, one more note is that the calculated probability of failure is a function of time. So the increase in risk over time can be simulated. So for example, what you see here, we can actually simulate over the following years, what is the increase in risk. That means that for the equipments that were evaluated to be low risk currently, it is possible to project into future years when that risk will exceed the allowable threshold. And that will allow for more proactive maintenance and inspection planning. And then, well, coming back to that first incident I showed of the 18-inch steam main rupture in the petrochemical plants. Actually, from the investigation reports, we can identify roughly what is the system configuration as well as the conditions before the incident. And then making some assumptions, we can perform a quantitative risk assessment for this section of the steam piping to estimate what was the risk of failure due to water hammer. If we plot the results on the risk matrix, we can see that at a point in time, 6 months before the water hammer incident, the risk would have been evaluated to have been extremely high. And then using the same methodology, we can also simulate the reduction in risk if corrective action was taken. In this case, the corrective action was simply to replace 2 of the steam traps that were located at very critical points in the piping. And we can also express this reduction in risk in terms of a financial term, which was equivalent to more than $6 million when considered over a 5-year period. So this demonstrates that a risk-based approach in this example would have been very effective and could have even been possible to help to avoid this kind of incident from happening. I'm going to hand over now to Justin is to go through some more detailed examples, some more detailed case studies of how we applied this risk-based methodology for steam systems. Okay, over to you, Justin.
All right, Alan, thank you very much. Just 1 second here. All right. Thank you, Alan. I just wanted to extend a thank you as well for everybody else joining us here today. Thank you for taking the time out of your day, of your busy days, I'm sure, to join us and listen about the updates to the API 581 4th edition, as well as the TLV's SSRM software. So this next half, what I'm going to do is go through some case studies and provide some guidance on how SSRM can be utilized in your plant. So we have 3 case studies to review. So we'll have a flare and its associated steam supply header. And we'll discuss some of the unique challenges that can make flares prone to high risk of failure. Talk about a reboiler. In this particular example, we'll look at a reboiler that utilized an outlet level drainage device and had a history of severe water hammer. And finally, we'll talk about a small single stage turbine. Actually, let's start with this turbine. So if you include the steam line piping immediately upstream and downstream of the turbine, you'll find there are several critical drainage locations. It's important to note that, of course, not every turbine is designed exactly the same way, so it's important to identify the low points where condensate can collect for the turbines in your plant. But for smaller single-stage turbines, especially with steam inlet control valve and exhausting to a low-pressure steam header, like I'm showing here, then these are the typical drainage points. So starting from right to left, first we have a separator drain trap, followed by the inlet and outlet drains at the steam supply control valve. Next we have a trap, sometimes multiple traps at the steam chest or trip and throttle, as well as traps at the inlet and outlet turbine casing. And finally, we have a trap at the exhaust pipeline. So for our particular example here, I'll just use a simplified graphic you see on the right side to kind of help follow us through what's going on. So I'll show you all the drainage points in this particular example and show you where things went wrong. So first, I'd like to point out that with this turbine, it actually did not include a moisture separator. So it's already at risk for blade erosion and potentially performance deficiencies if the steam supply has a low quality, or meaning that there's condensate entrainment or the steam is wet. And note that this is totally independent of any of the steam traps that we're talking about related to the turbine itself or the piping. So first 2 traps are on either side of the steam inlet control valve. One was good, the other one was leaking. So not too bad so far. Next, we're going to focus on the trip and throttle. So you'll see in the image, there are actually 2 distinct drain points on the trip and throttle. But each of these are going to serve to protect the valve and the inside parts of that turbine. And if you look close enough, you'll see that the valves that would drain condensate are actually closed. So it is preventing the passage of condensate from either section of this trip and throttle. Similarly, there's a closed valve on the inlet side of the casing. Fortunately, the outlet casing drain utilized a free float trap, which was in good condition. Finally, if we move to the exhaust side piping, you'll see yet another valve that's closed. So again, preventing passage of condensate from the exhaust piping. So of these 7 drainage locations on this turbine, including the associated inlet and outlet piping, there are really only 3 locations, including the leaking trap at location B, which are actively draining condensate. So for some people, you might be thinking, well, what's the big deal? You might be thinking that, hey, Justin, when a turbine is operating, there are high velocities, and that should help prevent accumulation of condensate. Sure, that might be correct, but in this particular turbine, it actually happened to be on hot standby, meaning that it wasn't actually in use. So it was paired with an electric motor that was in operation. So steam was still supplied to the turbine itself to keep it hot, but steam wasn't actively flowing through the turbine. So at this moment in time, the turbine was more or less a dead leg, where steam will condense and water will eventually fill the equipment until it reaches a location where condensate can be drained out. But hopefully it's clear that the lack of active drainage in this turbine and associated piping, it's a problem, especially while it's on hot standby. Now, to complicate things a bit more, this turbine utilized an unsupervised and automatic startup function. So this can be extremely beneficial for plants trying to manage their steam and electricity balance, but when a piece of equipment like this, which requires a dry steam space for a smooth startup and operation, but it's instead probably full of condensate, then an automatic and unsupervised startup of this turbine is likely going to result in a turbine trip and potentially cause a lot of damage to this turbine. So based on our evaluation, we assessed the risk value as shown here by that blue dot in the middle of our risk matrix. In order to mitigate the risk we identified, there's a couple very standard but critical actions to perform. So first, we want to install steam traps at all the locations with no current drainage. So that's going to be all the locations that we identify with a closed valve. And this is, of course, going to help to ensure that condensate is being actively removed from the low points in the piping and in the equipment. Otherwise, we might get into a situation where we have a turbine trip or some other type of damage. Next, we're going to want to install a high efficiency moisture separator and drain trap upstream of the control valve. Now, depending on the design of the separator, this could help to remove up to 98% of entrained moisture and may even be able to help remove high-speed condensate slugs that could otherwise cause significant equipment damage. So those 2 mitigation actions are going to help to significantly lower the risk, as you can see there, to the tune of about $70,000 US dollars in a 5-year period. So this risk mitigation merit, it might seem small to you, it might seem very high. It's important to keep in mind that both the consequence of failure as well as the adjustment of the probability of failure is what gives us the mitigation merit value. So in this example, the consequence of failure is about $1 million US dollars, whereas a larger, more critical turbine may have a much higher consequence of failure and therefore would have a much, much larger 5-year risk mitigation merit. All right, so let's move on to the reboiler. So for those of you that are familiar with reboilers or other types of steam and tube process heaters, you'll know to expect a differential pressure across the steam space, meaning that as steam passes through the tubes, steam pressure is lost, often such that the outlet pressure is 2% to 15% lower than the inlet pressure. So if we're using, let's say 100 PSI, then potentially the pressure on the outlet side could be 85 PSI. So many reboilers utilize one form or another of outlet level drainage. The one you see here incorporates a level pot and requires an equalization line. And that's going to help displace vapor as the liquid level inside the level pot rises and falls. However, we often find that equalization line is routed to the steam inlet piping like you see here. So if you imagine that and then combined with a large pressure drop through the steam space, we're going to encounter a scenario where condensate is going to have to drain from the reboiler steam space against a higher pressure than originally intended. And so when this happens, condensate's often unable to drain from the steam space fast enough, sometimes if at all. And so that's going to eventually lead to an accumulation of condensate inside the steam space, typically resulting in poor process control and water hammer. So with our real life example here, we can see the exact same thing occurring. We have the steam supply and the condensate discharging to an outlet level pot. You can see how the equalization line is connected to the steam supply. So on site, we could tell that there were problems just due to the significant temperature difference measured at the equalization line compared to the temperature we were reading at the condensate discharge. So you see at the top, 443 degrees Fahrenheit at the equalization line and about 330 degrees Fahrenheit at the condensate discharge. So a little over 100 degrees Fahrenheit. And when we see a dramatic temperature difference like this, it's usually a clear sign of condensate accumulation inside that reboiler or steam space. And then after speaking with operators, their operations team, what we found is that there's also a history of water hammer. So we suspected there would be water hammer and found out that there really was water hammer. They also expressed a history of difficult process control, and they even suspected a degradation of the heating surfaces. While on site, what we also found was that the outlet control valve was 100% open with 0 level in the level pot. On top of that, quite a bit of erosion and corrosion and condensate leaks in the condensate recovery piping. So what the operations team decided to do to mitigate their problems is that they were going to discharge all the condensate to the sewer. So the interesting thing about this particular decision is that in doing so, they were able to help mitigate most of the water hammer, but it didn't actually solve any of the issues related to the poor process control. Since I'll call it short circuiting of the high pressure steam, bypassing the tubes inside the reboiler, were able to easily make its way to the outlet. So it still created a very difficult pathway for condensate to be discharged through that reboiler. So considering all these problems, we assessed the current risk value. It's represented here by that blue dot. And it might be obvious, but the recommended mitigation action was to reroute the equalization line to a lower pressure steam space on the reboiler. Now, fortunately, in this case, they were able to utilize an existing tapping on the channel head to reroute the equalization line to that lower pressure steam space. Now, this isn't always the case. Sometimes we find that there is a tapping. Sometimes we find that there's not a tapping. Sometimes if there is a tapping, it might be connected to other piping and it's utilized for some other purpose. But this was at least one pathway that we could go to fulfill this mitigation action. So in doing so, sort of like what you see here, condensate is able to freely drain from the level pot and from the reboiler itself, helping to mitigate the accumulation of condensate and help the reboiler operate as it's intended. But on top of that, the plant personnel really should evaluate the condition of the heating surface for any fouling, any corrosion, as well as check the condition of the outlet level control mechanisms to make sure that those are working properly. And then, of course, perform any repairs necessary to help restore the originally intended operation of the reboiler. Finally, closing that outlet blowdown valve is going to help to allow the plant to recover that lost live steam and condensate. So performing all these mitigation actions is going to lower our risk assessment, helping to provide a 5-year risk mitigation merit of nearly $1.3 million US. As a bonus, closing that outlet blowdown valve, now helping prevent the loss of steam and condensate to the atmosphere, will actually earn an additional merit of about $30,000 to $40,000 annually. So big win here. Seeing how the updated guidance of API 581 and maybe SSRM can be applied to steam systems, I really hope you're beginning to ask yourself, how can I begin applying risk-based inspection to my steam assets? So my answer is TLV is more than happy to help. And we'd like to propose utilizing TLV service of SSRM or Steam System Risk Mitigation. We've covered examples of applying SSRM to a steam turbine, looked at a reboiler, looked at a flare. But beyond that, we can also apply SSRM to vacuum steam systems, which would include steam injectors, as well as the inter and after condensers of vacuum systems. We can apply it to tracing systems, whether it's tube tracing, process pipelines, like you see here, or if it's jacketed piping, like what's often seen in sulfur recovery units, or instrumentation tracing, which sometimes can be extremely critical to operation of a manufacturing plant. And we can apply it to any and all steam distribution headers and condensate recovery headers. So of course, it's one thing to perform a risk assessment of individual equipment, but combining this analysis of an entire area or of an entire plant on a single matrix can really help us to understand the highest risk areas. It's going to help to prioritize where to focus your efforts in reducing that risk. And so SSRM can also help with evaluating the impact to risk of different mitigation strategies. So we're able to compare the change in probability of failure with different strategies. So like you see plan A here on the left, plan B on the right, and then weigh this against the cost of implementation to determine what is the best return on our investment. And now TLV's larger objective and goal is we really want to help our customers optimize their steam systems. So performing risk-based inspections on steam systems like with TLV's SSRM or Steam System Risk Mitigation software, that's certainly going to help highlight and quantify specific pains within your plants, and it can help to resolve the best path for mitigating those pains. But we strongly encourage to pair this with a robust condensate discharge location management program, and that's going to help maintain a minimal or ideal risk level at your plant. And then further, if we pair that with the steam balance or steam application survey to focus on things like energy management or condensate recovery, then really putting this all together, the absolute best approach to creating a plant-wide steam system optimization program and fully optimizing your steam system. So that's it for the presentation for me here. I just want a couple quick things to let everybody know that, as Norm mentioned earlier, most of us presenting today, excluding Alan, we're located in North America. If you have any questions, please contact us. You can reach out to us at 1-800-TLV-TRAP, or you can email us at ces@tlvengineering.com, and we're happy to discuss your applications, happy to help as much as we can with your steam systems. And of course, recognize that we have a very big global audience today. We do have 14 global offices. So as your calls and questions come in, we'll be happy to either answer those directly or route you to your local TLV representative from the region of the world that you're living. And also encourage you to visit our website. We have an online calculator, technical articles, articles which you can find. They're in the handout section of this webinar, as well as past webinar recordings. So again, I want to thank everybody very, very much. And at this time, I'm going to turn back on my webcam. I ask that Alan, Alec, and Norm please do the same thing. And you'll have to unmute yourselves as well.
Right. All right. Alec, you want to go ahead? I saw there were some questions coming in while we were presenting here. So you want to moderate that?
Right, absolutely. And fantastic presentation, Alan, Justin. We had a lot of great questions coming in throughout the presentation. So for everyone tuning in, thank you for your participation. I'd like to share a couple of those questions just during our Q&A portion. Justin, how long does a SSRM assessment usually take?
So it's going to depend on, of course, how many assets or piece of equipment we need to review. So typically we can review 5 to 10 in a given day, depending on what the actual application is. So depending on the application and then the quantity of those, maybe it's a day, maybe it's a week, could be more total. So it's really dependent on what the scope of work is. Right.
Yeah, I'm sure the complexity of the equipment or system will really impact the duration. Alan, how does this assessment fit into existing RBI programs?
Well, existing RBI programs, they may or may not be already covering the steam using equipment or things like steam distribution mains, which are really what is the focus that we are looking at here. So if they are not covered under the existing RBI program, doing this kind of assessments, it will of course add on this equipment to the asset list that can be managed from a risk-based point of view. Even if you have steam equipment or even steam mains that are already being covered under your RBI asset list, this kind of assessment that we covered today, it actually complements your existing risk analysis, because existing RBI, it's looking at different damage mechanisms. So what we are looking at here is from a steam system point of view, accounting for the damage mechanism of things like water hammer that we showed. So that gives a more complete risk profile for your overall assessment.
Yeah, thank you for that. And one last question, Justin, what's the difference between SSRM and the API 581 method?
Great question. So I guess first comment is that, as we highlighted earlier in the webinar, SSRM is explicitly following the guidelines in API 581. So there's no difference technically, but there are, as Alan presented, there are base case type methods that without extensive data or things that you can relate to your own equipment on your plant to have more accurate data, you can use the base case probabilities of failures and the Weibull curves to apply to the method to still follow SSRM. But with the extensive database that TLV has of steam traps, we have a much more accurate way to assess the probability of failure of traps, and therefore a much more accurate way to assess the probability of failure of the steam asset as a whole, to understand what the actual risk is.
Right, thank you.
Okay, well, Alec, thank you for moderating the Q&A. There were a couple of questions I still see coming in. If we did not get a chance to respond to your question during the broadcast today, we'll follow up with you directly. There were also a couple of very specific application questions that came in. So we'll be following up and also getting our local teams involved, understanding more about your application and your plant. I did notice when I was looking at the registration list, ahead of time, as we've been watching hundreds of people sign up for this. And again, thank you for tuning in. Many of the folks attending are our friends, people we know in the utilities section, and people that we deal with in process engineering. I would ask you all to also bring this topic up with the inspection groups inside your organizations. You know, Alan touched a little bit about how this complements and really fits into your existing RBI programs. You know, that's what this is all about. The 581 guidelines been expanded now to include the STEAM assets. You know, everybody wants one comprehensive program for their site and their facility. Anyway, please bring this up with your inspection groups and get it on their radar screen. If it's not already, they can certainly look and watch this webinar, and we'd be very happy to come in and discuss this with you all directly between the utilities groups, engineering teams, and the inspection groups about implementing this at your specific site. So again, I want to thank you for tuning in today. We will be posting today's webinar to the TLB website. It takes us a few days to format the video and have our web team do their thing to pretty it up a little bit and put some more TLB logos and things in there. And but take a look for that next week. And again, I want to thank you all very much for tuning in today. And we will be broadcasting again just in a couple of hours at 2 p.m. Eastern time today. So thanks again for tuning in. And we look forward to discussing this topic with you directly very soon. Take care, everybody.
Thank you.
Thank you.
Thank you.